Great. Nice start.
Okay. Hi everyone, I'm Kevin. So I'll be hosting today's online tutorial. And today we're gonna recap some key concepts of causal inference that we'll talk about in the lecture. And also we'll walk through some practical examples and exploring how we can use the causal tools such as the backdoor and frontal criteria to understand the causal relationships in the data. Okay, so let's begin by review the Markov condition. So typically we separate the Markov condition in two levels, which is the local Markov condition and the global Markov condition. So the first concept is the local Markov condition, and this condition is a key property of directed acyclic graphs, or we also call it DAGs, and it helps us to understanding the conditional independence relationships among the variables in the graph. So the local Markov condition states that each variable in DAGs is conditionally independent of its non-descendants, and given its by given its parents. And essentially, if we know the parents of a variable, then we do not need to any additional information about its non-descendants to predict the variables. So let me explain this concept by using the example graph shows right here. So in this graph, we have several nodes. So let's firstly focus on the node X. So the node X have only one parent, which is a T. So according to the local Markov condition, the X is conditionally independent of all the nodes that is not its descendants if we already know its parents T. So in this case, X is independently of the Y and W by given the parents T. And this property is very useful because it allows us to simplify our analysis by reducing the number of relationships that we need to consider when we are trying to understanding a specific variables. And instead of considering every possible variable in the graph, we only need to focus on its parents. So the second concept is the global Markov condition, or we also call it D-separation. So D-separation is another crucial concept in causal inference that help us to determine if two variables are conditionally independent given a set of other variables. So let me first give you the formal definition. So a path between the node X and Y is blocked by a conditioning set Z if one of the following condition holds. So first one is that along the path, there's a chain structure or the fork structure, and the W is in the conditioning set. And the second one is that there's a collider structure, W on the path, and the W is not in the conditioning set. And none of its descendants are in the conditioning set. So now let's apply this definition to our example graph. So we can have a better understanding how the D-separation works in the practice. Let's consider the path between the T to a W. So which is this path. So the path Tx z y w, and in this path we have the z, which is a collider because there's a two arrow converge on the one is from the x and one is from y. And according to the definition of the D-separation, so this path is blocked if the z is not conditional, and none of the z's descendants are conditional. So however, if we condition on z or one of the its descendants, the path is become unblocked. So let's look at another example. So let's look at a path from S to W, which is this path. So here we have Z is again a collider, and if the Z is not conditional, the path remain blocked it, which preventing any information from the flowing between the S to the W. And however, if we can condition the Z or its descendants, the path will become unblocked again. So this separation is crucial because it allows us to determine whether two variables are independent given some other variables. And this helps us to figure out what variables to control for when we want to remove confounding influence. Okay, so let's go through an example. So which can help us to illustrate how we can use this concept in the causal inference. So this problem we are going to discuss is the kidney stone problem that we already talked about in the lecture. And in this example, we have two treatments for the kidney stone. One is the treatment A.
Sorry, Kevin, sorry. For
Yep.
that path, they is the collider.
Yeah.
Yeah, for that one. So suppose we also include
For
X.
like which path you means?
All right, so here we have this one. Suppose we care about the
Yeah.
conditional dependence between T and W.
Yeah.
So if we condition on Z,
Yeah.
so T and W will be conditionally dependent, right?
If we consider the Z in the conditional set, then this is not independently between the Z T and W.
Yeah, so if we further condition on X,
Yeah.
so in this case, whether T and W are independent.
Oh, yes, if we have the condition set which is C and X, and this will be conditionally independent again since this path is blocked by this one. This is a chain.
Yes, great. Also, you have explained this, right?
Yeah.
All right, great, great. That's great. Thank you.
So let's continue by the example. So in this example, we have a two treatment A and treatment B. And the outcome we are interested in is the recovery, which donate R right here. And the size of the kidney stone, which donate S right here, which can be either small or large. So our goal is to determine which treatment is more effective while taking into account the stone size. So here we have our data, and we are trying to calculate making the observation probability first. So we have success rate and a group proportion in the data of different treatment and the stone size already. So for treatment A, with the stone size, the success rate is approximately 93% with a large stone size and 70 for the small stone size, and for large stone size, which is 73. So for treatment B, the success rate is 87 for small stones and 69 for large stone size. And by using this number, we can calculating the overall recovery probability for both treatment. So let's first think about the treatment A. So we have our probability of a recovery when the treatment equal to A. And we can use the chain rule to decompose this probability, which will become the sum, like given the stone size, which can be small and large, and the probability of recovery by given the treatment equal to A and the stone size times the probability of the stone size by given the treatment equal to A. So by substitute the data back into this decomposition, we can have 0.93 times 87 divided by 355. The 355 means the total number of patients both in treatment A and treatment B, and plus the 0.73 times 263 divided by 350. So this is going to be approximately 0.78. So we have 68% right here in total. So let's consider the probability for the treatment B in the same way. So it's going to be 0.87 times 270 divided by 350 plus 0.69 times 80 divided by 350. So this is going to be around 0.83. So here we have 83%. So in here, based on this analysis, it appears the treatment B is more effective. But however, this conclusion does not consider the potential confounding effects of the stone size. And if we only focus on the observational probability, and this is also known as the Simpson's paradox. And okay, so next let's use an intervention analysis by randomizing the treatment. So by doing this, we ensure the stone size is distributed independently of the treatment. The reason why we use the interventional analysis is because the golden standard is not always feasible. So we need to use other ways to simulate the randomized control experiments. So firstly, we assume the stone size distribution remain the same across the treatment. So our marginal probability for the both stone size, which is small, the probability of small will be 87 plus 370 divided by 700, which is the total patients in this experiment, so which is 257 divided by 700. And we have our probability of the large stone size, which is the 263 plus 80 divided by 700, which is 243 divided by 700. So now let's calculate the recovery probability for each treatment after the adjustment. So we have our probability of recovery by the intervention to the treatment of the treatment A. So we use the same decomposition as we did before. Firstly, so which is the TQT, sorry, TQA times the probability of S if we make it A. So since we assume the probability for the both treatment, the distribution is the same. So which means that for this probability, it is regardless with the treatment. So we're gonna replace here into the marginally the marginal distribution of the stone size. So finally, this is gonna be for the treatment, it is gonna be 0.1 87 times 357 divided by 700 and plus 0.69 times 343 divided by 700. So this is gonna be 0.83. So we do the same things to the treatment B. And this is gonna be 0.93 times 357 divided by 700 and plus 0.73 times 343 divided by 700, and which is gonna be 78%. So we can see after the adjustment, the treatment A is actually turned out to be more effective. And this illustrates the importance of considering the confounding variables like the stone size before drawing the conclusions. So let's continue by looking some other key concepts. So let's move on to the backdoor criteria first, which is very important in causal inference. The backdoor criteria helps us to determine if we can properly estimate the causal effect of the treatment on the outcome by adjusting for a set of variables, W. So, here's a formal definition for the backdoor criteria. A set of variable W satisfies the backdoor criteria related to the treatment and the outcome if the following conditions are met. So first one is the W blocks all the backdoor paths from the T to the Y. So we can draw the DAG by this notation. So it is like this one. This is a treatment, and this is the outcome, and this is the confounders. So for the first one, we said a backdoor path is a path from the T to the Y that start with an arrow pointing to the Y. So this one, so we can see here, this one is a backdoor path, and the W block the backdoor path right here. So the second condition is that the W is not contain any descendants of T. So if a set of variable W matches these conditions, then we can use it to adjust for confounding and accurately estimate the causal effects of T on Y. And the adjustment formula is given by here. So in this formula, the PW represents the probability distribution of the confounding variables, which affects both the treatment and the outcome. So we can then calculating this probability, which is the conditional probability of the outcome given by the treatment and the value of the confounder. And by using summing overall possible values of the confounder, we effectively block the backdoor path that will be introduced by us. And this adjustment ensures that we are estimating the causal effect of the treatment on the outcome, as if the treatment has been randomized, so removing any confounding inference that could be otherwise distort the conclusions. So let's connect this back to the example that we talked about before, the kidney stone problem. So in this example, the variable representing the stone size act as the co-founder, and the stone size affects both of the treatment selection T and the recovery. By adjusting for stone size, we effectively block the backdoor path between the treatment and the recovery, allowing us to estimate the true causal effect of the treatment on the recovery. And this backdoor adjustment is crucial for removing the confounding effects that could be otherwise led to biased conclusion. Okay. So now let's move to discussing the frontal criteria. And typically we use it when the backdoor criteria is not satisfied. And which is useful when we have a mediator that fully explains the causal effect of the treatment on the outcome. So here's a formal definition. A state variable M satisfy the frontal criteria relative to the treatment T and the outcome Y, if the following conditions are true. So we have three conditions right here. The first one is that the M is completely mediate the effects of the Y on T. And in other words, all the causal paths from Y to T go through the M. And the second one is that there's no unblocked path from the T to the M, and all the backdoor paths from M to Y are blocked by T. So if mediator M meets this condition, we can identify the causal effects of T on Y and using a frontal adjustment formula right here. So in this formula, we first calculate the probability of the mediator M by given the treatment T, which is this probability. And this step capture how the T affects the mediator. And then for each possible value of the mediator, we estimate the probability of the outcome Y by given the mediator and the hypothetical treatment. And while integrating overall the distribution of the mediator. And the idea is that to piece together the effect of the treatment on the mediator and subsequently the effect of the mediator on the outcome, which allowing us to derive an overall estimate of the causal effect of T on Y. And this two-step estimation is essential for isolating the causal pathway through the mediator. So let's go through by looking at this diagram. So the arrow and the path in the diagram will help us to understand how the frontal criteria works. So we can see that the variable M act as a mediator, and which linking the causal relationship from the treatment to the outcome. And this causal relationship is represented by the blue arrows, meaning all the causal paths from T to Y pass through the M. So M pre-mediate the effects of T and Y, satisfying the first condition of the frontal criteria. And the diagram also shows another variable W, which is a potential confounding variable, and it affects both the treatment and the outcome. So, however, by adjusting the mediator M, we can isolate these confounding effects, and which can ensuring that we can actually assess the causal effect from T to Y. And using a frontal criteria, we first estimate the effect of a treatment on the mediator, which is the conditional probability of the mediator by given the treatment, which is the P of M given by T. And then we estimate the effect of the mediator on the outcome, which is the P given by outcome of the mediator and the treatment. So by doing these two steps, we can able to inference the causal effect of the Y to the Y on from T to the Y correctly. So let's illustrate this with a concrete example. So suppose we want to analyze the effect of advertising on the sales, and we believe the customer interest is the mediator. So in this scenario, the customer interest fully mediate the effects of advertising on the sales. So advertising increase the customer interest, and which in turn derive to the sales. Additionally, there's no unblocked path from T to M, and all backdoor paths from the M to the Y are blocked by the T. So using the frontal criteria, we can estimate the causal effect of advertising on the cells by first estimating the effect of the T on M, and then estimating the effect of M on Y. This allows us to control the confounding that maybe otherwise influence the customer's interest and sales directly, indirectly. So, okay, so now let's go through some practical question that can help us to better understanding these two concepts. First one is about the example for the backdoor criteria. So the scenario is that we are trying to studying the effect of additional training on the employee's performance. However, the experience level is an confounder that affects both training and the performance. So the DAG is representing as the following. In this DAG, the E affects both the both the training and the performance, in which indicates the experience level plays a role in determining whether an employees receive the training and how they perform. So we have two tasks right here. So one is the does the E satisfy the backdoor criteria? So to satisfy the backdoor criteria, a variable set W must be block all the backdoor paths from T to the R, and the W should be not a descendant of T. So in this case, the experience level E block the backdoor path from the T to R. This one is a backdoor path, and we specifically this path is the TE R is a backdoor path that could be introduced the bias, and since that E is not a descendant of T, it means that the conditions of the it meets the conditions of the backdoor criteria. So so that the conclusion is that the E satisfy the backdoor criteria. For the second task, we are trying to estimate the probability the conditional probability of the R by doing the intervention to a T. So we can use since it is satisfied the backdoor criteria, so we can use this adjustment formula to do this question. And right here I already give you some basic data. So let's firstly calculating the probability of the R by giving the T equal to 1. The 1 means that in this scenario, the T equal to 1 means that we do give it additional training. So by substitute the data into this formula, it's gonna be 0.7 times 0.4 plus 0.9 times 0.6. So which is gonna be 0.28 plus 0.54, which is equal to 0.82. So we need to calculating for when we do not give it additional training. So in here, which is 0.4 times 0.4 plus 0.8 times 0.6, which is equal to 0.16 plus 0.48, which is equal to 0.64. So the conclusion is we can see the training improves the employees performance significantly, since it shows the increase in probability from 0.64 to 0.82. Okay, so the second one is an example for the frontal criteria. So we're using the same scenario, which is we want to study the effects of advertising on the sales, but we have a mediator, which is a customer's interest that affects that's between the advertising and the sales. So additionally, there's an unobserved confounder, which is U, that affects both of the customer's interest and affects both of the advertising and the sales. And the DAG is shows right here. And the task is the same as above. So first things we need to determine if the Z is satisfied the frontal criteria. So remember to satisfy the final criteria, we have three different conditions. So the first one is that the Z must be fully mediate the effects of the T to R, and meaning that all the causal paths from the T to R must be path through Z. So for the first condition, this one is satisfied. And the second one is that there should be no unblocked backdoor paths from the T to Z. And in this diagram, there's no backdoor paths from the T to Z. And all the backdoor paths from the Z to R should be blocked by the T. There is a backdoor path from Z to R, but this one we can see the T is exactly blocked. So which concludes that alpha Z satisfy the frontal criteria in this situation. And we need to do the second task. The second task is that we need to calculating the conditional probability of the cells. So by using the frontal criteria right here, we given the formula, given this formula, and this is a simplified version of the full frontal adjustment formula. And instead of summing overall possibility treatment, we directly use the relationship between the advertising, customer interest, and the sales to make our calculation more straightforward. So here we assume that once we know the effects of advertising on the customer interest, which is this probability, and the effects of a customer interest on the sales of this one, we can determine the overall effects without the additional complexity. So this simplification works well in the context because the assumptions are fairly direct, making it easier to estimating the effect without losing much accuracy. So now let's try to calculate this by this given data. So firstly, we need to calculating the sales when we do not given the advertising. So in here, you can see which is the sums of 0.7 times 0.3 plus 0.3 times 0.8. So which is 0.21 plus 0.24, which is 0.45 right here. So we need to calculating the probability when we given the advertising also. So which is 0.4 times 0.3 plus 0.6 times 0.8, and which is 0.12 plus 0.48, which is 0.6. So in here we conclude that the advertising increase the sales with a probability of success increase from 0.45 to 0.6. So this is two examples for the key concepts. And we do have another example. So this is a revision for a previous one. So for this question, we revise the key example to verifying the backdoor adjustments. So for the first question, to satisfy the backdoor criteria, the confounder must be block all the backdoor paths from the treatment to the outcome. And obviously from previous DIG, we can see by conditioning the size, it is actually block all the backdoor paths from the treatment and recovery. So it satisfies the backdoor criteria. The second one is that we are doing the same things that calculating the condition probability of a recovery by given the treatments A and B. So in here we assume the marginal probability for the stone size which are the same, so which is 0.5 right here, and we need to calculate in both of the recovery by given the treatment which is equal to A and B. So remember the formula that we used before, which is the as given by small and large, which is the probability for recovery by given the t given t and the stone and the probability of the stone. So for this one, which is equal to so for this one, which is equal to 0.93 times 0.5 and plus the 0.73 times the 0.5, and which is equal to 0.83. So we need to do the same things for the recovery by given the treatment B. So which is 0.87. So here's the 0.87 times 0.5 plus the 0.69 times 0.5, and which is 0.78. And this also concludes that after adjusting the stone size, the treatment A is more effective with a recovery probability of 0.83 compared with the 0.78 to a treatment B. Yeah, and I think that's all for today's online tutorial. So if you have any more questions, feel free to ask via ED so we can answer you properly.
Great. Thank you, Kevin.
Yeah, thank you very much.